Neural Inertial Localization. Recent advancements in deep learning allow us to infer robust relative motion trajectories from IMU sensor suite, a task known as inertial navigation. Inertial localization, the task of estimating the global location from IMU sensor data, is possible, for example, by finding a suitable placement of a motion trajectory with a flow plan. However, this process is slow, requires a flow plan, and is susceptible to sensor bias, resulting in large errors in the integrated motion trajectories. We introduce neural inertial localization, where we use autoregressive transformer-based neural architecture to predict the location from a history of IMU data only, without the use of a flow plan. We focus on NILoc, which enables location-aware services on smartphones, AR/VR devices, or wearable devices such as a smartwatch, and can extend to any building, be it a commercial space or a home. GPS location from a smartphone allows us to navigate effectively in outdoor environments but fails indoors. Current indoor positioning systems depend on images, Wi-Fi, or IMU data sources. Image-based localization has high accuracy but is energy draining and reveals data about the user and bystanders. Wireless localization is not as precise but has similar drawbacks. In contrast, IMU data is energy efficient and doesn't contain any user information. IMU data combined with flow plan information or predetermined activity location mapping has been used for localization previously. In this research, we present the inertial localization problem, introducing a compelling alternative data modality, the first inertial localization dataset, and a neural inertial localization algorithm. Input to inertial localization is acceleration and angular velocity data relative to the device provided by the inertial measurement unit or IMU. We estimate the location of the subject in a known environment only from a history of IMU sensor data. The secondary task is inertial relocalization, where the initial location or initial pose is known a priori. This is the scenario where IMU acts as a complementary data modality to wireless or image data. We present the first inertial localization dataset containing 53 hours of motion data from one office space and 2 university buildings. Each sequence contains IMU sensor data and ground truth locations from visual inertial SLAM. We present NILoc, a neural inertial localization model. We use a neural inertial tracking algorithm, RONIN, to compute relative velocity vectors from IMU sensor data. We resample velocity vectors based on the distance of travel to reduce uncertainty. Our transformer architecture contains 2 transformer-based network branches. The velocity branch estimates a location sequence given a sequence of velocity vectors. A temporal convolutional network compresses the temporal dimension. Transformer encoder computes self-attention among input features, and translation-aware location decoder upscale each feature volume to the map size of a building to give location likelihood at each time step. The autoregressive location branch combines the velocity features from the velocity branch and prior location likelihoods. Prior likelihood at the first frame is a uniform distribution over map for localization task or external position information from wireless or visual SLAM for relocalization task. The likelihood map is compressed via 2D CNN. Transformer decoder computes cross-attention among prior location and velocity features. Translation-aware location decoder upscales each feature volume to the map size of a building. For all subsequent frames, we use all predictions as prior locations. We calculate cross-entropy loss against ground truth location for each branch at each time step as supervision. We will now present qualitative visualization. Ours is the first work addressing IMU-only localization. We compare against 3 baselines that require a floor plan input in addition to IMU. We show the predicted likelihood map of each method. The time axis of video is proportional to the distance traveled since we perform distance-based sampling as an input pre-processing step for all methods. Particle filter updates a set of particles, each of which stores the location, hiding direction and error correction terms according to IMU input. The floor plan is used to reweigh and resample the particles. Learn prior is also a particle filter-based approach while using deep networks to help update particle weights. A location likelihood computed by the dot product between floor plan features extracted by unit and motion features extracted by LSTM is used to weigh the particles. Conditional random field baseline computes a reachability graph from a floor plan, uses inertial navigation results to transition between graph nodes, and the Viterbi algorithm to backtrack and determine location. Nylock produces a likelihood map for each time step only from IMU data. We use the output from the location branch produced using a sliding window along IMU input. First, we demonstrate the inertial localization task. We visualize one example trajectory from each building. Learn prior method requires starting pose and therefore cannot perform inertial localization. Nylock achieves the best results in most examples. The second best method is conditional random field algorithm, which uses floor plan information and is computationally intensive. It is 30 times slower than our method since it effectively searches for all possible alignments with the floor plan exhaustively. Particle filter exhibits poor performance where the major challenge is high uncertainty from cumulative drifts in the inertial navigation trajectories. Another observation is that all the baseline methods explicitly integrates velocities to update the location information. In contrast, Nylock relies completely on powerful transformer-based architecture to relate macro-level patterns in velocities to locations. Please refer to our paper and supplementary material for quantitative results, ablation study and comparisons against other backbone architectures. Now we will show 2 examples for inertial relocalization, our secondary task. First, the starting location of the user is given. All methods consistently improve performance with more initialization information. Next, the starting pose, that is, location and orientation, is known. In summary, we present the novel research problem of inertial localization and a transformer-based architecture that learns location information from relative motion patterns. Our approach is significantly faster and achieves competitive results even compared with state-of-the-art methods that require a floor plan and run 20 to 30 times slower. We publicly share our code and data to promote further Indo-localization research. Thank you.